Hi, I'm Michael Kuchnik, and today I'm going to talk to you about progressive compressed records, which take a byte out of deep learning data. This is joint work with my advisors, George Amvrosiadis and Virginia Smith. To set the stage for the talk, I would like to ask a simple question. What is an appropriate level of quality for a machine learning dataset? On the left, we can see that there's a picture of a celebrity who is smiling. On the right, we can precisely say that the celebrity is John Stamos from the TV show Full House. We can intuitively see that there's a trade-off between image quality and the type of questions we can answer. The image on the left can answer questions such as if the person is smiling or not, but the image on the right may be necessary to identify the person. The question this work attempts to answer is how to build systems which can exploit such variability in data quality. If we zoom in closer on these images, we can tell that there are some significant differences. The image on the left is pixelated, while the image on the right is sharp. However, if we look at the space consumed by the image on the left, it's an order of magnitude smaller than the image on the right. Today, the standard choice is to always pick the highest quality image, which may become a problem when loading data itself is a costly operation. To understand why data loading can be expensive, I'll provide an overview of how training is often performed. To start, you get 8 accelerators, such as GPUs or TPUs. You connect them with a fast interconnect, and you mount a large capacity-oriented data source, which is backed by hard drives. The accelerator consumes a combined total of 1,024 images in a single training step. During each step, those images are partitioned, and each device calculates gradients to improve the model. The gradients are summed across the devices, and the final gradient is applied to the model. The compute step occurs 10 times a second, which means that with pipelining, the storage system is supposed to be reading over 10,000 images a second. To see how this trend changed over time, we will examine standard ImageNet training over a range of accelerators. On the x-axis, we can see 3 generations of TPU accelerators ranging from TPU v2, which is over 5 years old, to the TPU v4, which is in the process of becoming publicly available. On the y-axis, we can see the amount of time in milliseconds it takes to train over a single batch of 1,024 images. For demonstration, we fix the storage bandwidth to 1 gigabit per second. We then calculate the amount of time necessary to load 1,024 images and plot that with a red line. We can see that it takes about 100 milliseconds to load this many images. From there, we will use 3 depths of models, ranging from ResNet 50, the most complex, to ResNet 18, to see how the combination of accelerator and model affects the total time to train over a batch. In blue, we have the compute time, which is the time necessary to compute over one batch. And in red, we have the load time, which is the slowdown incurred due to being bottlenecked by 1 gigabit per second of storage bandwidth. We can see that the TPU v2 takes over 200 milliseconds to compute a batch with ResNet 50, while ResNet 18 takes just around 100 milliseconds. None of these are slowed down by the storage bandwidth. However, the story changes as we begin using the faster TPU v3, which is roughly 2 times faster across the board. We can see that both ResNet 34 and ResNet 18 are spending between a third and half of their total time waiting on data. As we go to the TPU v4, which is the most recent, we can see that all models are projected to be storage bound in this configuration. Therefore, we can conclude that faster accelerators and more efficient models will present storage challenges. So to summarize, the main problem we seek to address is how to minimize the storage bandwidth required of deep learning training. Our approach is to reduce storage bandwidth with a novel storage layout that allows compression to be applied dynamically. Now we'll switch into describing machine learning data layouts, which are used to feed these accelerators. On the x-axis, we show the logical storage address of a disk, which one can think of as the mapping between a disk and the file system. We will visually display files across this range to demonstrate the various layouts. For demonstration, we show 3 files scattered throughout the logical storage address. The location of each file and its length are represented by rectangles. What we want to analyze is how each layout performs on a per batch basis. Shown here is the first thing one may try, having a file for every single image in the dataset. We can see that since each file is randomly placed across the address space, we may perform a random read for each file. The major downside of file per image formats, therefore, is that they perform very many random reads, which are expensive on hard drives. On top of that, they don't reduce bandwidth at all. If we move on to the current practice of using record formats, which group multiple files together into a single file, we can reduce the number of random reads. However, the bandwidth usage is still the same. Progressive compressed records, which we introduce, allow variable bandwidth usage while also performing sequential reads. The key difference between progressive compressed records and standard records is the same record can be read at multiple levels of detail. To implement progressive compressed records, the first thing one must do is encode images into a progressive format. For this part, we leverage progressive JPEG due to its speed, simplicity, and ubiquity. As shown on the right, the celebrity JPEG is broken up into 3 levels of quality, which we will refer to as scans. Each scan achieves higher quality than the previous scan. The next technique we use is to group images by the image quality, or scan number. On the left, we see 3 celebrity images that were converted into progressive format. Each row in this matrix is a file, and each column is a scan. On the right, we see the transposed version of that matrix, where rows are now the scans and columns are now the files. This is good since now we can do reads across the quality of the rows of the representation, which avoids random reads. Finally, the matrix is written out to the file system and an index is recorded in a database, such as SQLite or RocksDB. The index serves as a set of pointers for the serialized file, allowing for the scan groups and image offsets to be easily found. To read the progressive compressed records, we have to undo the grouping that was done previously. We start by choosing a group to read, such as scan group 1, and we look up the index for the scan group in the database. The database tells us to read the file until offset 90,000 and then stop, which saves bandwidth as we avoid reading unnecessary bytes. This gives us all the scan1 images in the record. Finally, we can ungroup the images in the scan group by using the remainder of the index. We can use the index to split the scan group back into 3 image files. At this point, the images can be processed by any machine learning framework. To evaluate progressive compressed records, we show ResNet 18 convergence over time. The x-axis is wall clock time in minutes. The y-axis is the top 1 test accuracy. Higher accuracy is better. We evaluate multiple loaders. As a baseline, we use a record format, TF records, and compare it against various scans of progressive compressed records. We can see that TF records reaches convergence in over 400 minutes. Comparing to scan 10, we can see that they reach nearly identical accuracy at nearly identical times. This is expected as both scan 10 and TF record consume similar bandwidth. When we switch to the lowest quality scan, scan 1, we can see that we get around a 2.5x speed up compared to TF record, but accuracy drops dramatically. As we move up to scan 2, we see a boost in accuracy over scan 1, but the training time is roughly the same since we are compute bound. However, when we drop to scan 5, we see that training completes in 200 minutes, which is a 2x speed up over TF record, and is within a percentage point of the original accuracy. This speed up is expected as scan 5 is half the size of scan 10 and thus uses half the bandwidth. While we do not show it in our plots, we also compare against file per image formats and find them 25 times slower than TF record formats. Such performance is expected for hard drives, which have a large performance penalty for using random reads. In the paper, we also describe how to perform auto-tuning using progressive compressed records. The intuition for how this is done is we compare the updates for each scan to regular training and only accept scans that result in similar updates. Such auto-tuning allows us to get most of the benefits of progressive compression without humans manually picking the image quality for the task. As shown on the right, training with auto-tune over ResNet 18 is nearly 2 times faster than TF records. This is because at Epic 5, training is stable enough to turn on auto-tuning, and auto-tuning switches to using the faster scan 5. We found it necessary to start with full quality data during this warm-up phase because low quality data can actually damage the model. For this talk, we didn't have time to cover everything we cover in the paper, but we encourage you to see the paper for how image quality interacts with the model and task, how to calibrate image quality with static measures such as multi-scale image similarity, and for further details and experiments. Thank you.